to derive another equation to solve the unknown. Okay, so today we look at conservation of forces. So when you have the word conservation added in front of the term, conservation force, it means the force is independent of the path it travels. Independent of path it travels. For example, the weight. You know that force will do work. You know that force will do work. Okay. Any forces, for example, W will do work. No matter how you move these particles, you move up or move down, the weight still pointing down. And to do work, you want to calculate delta U or U to do the work. You doesn't care the path that it travels. You only, what is work? U equal to force multiplied by vector of distance, or D. You only interested in this one. Okay, you only interested in this S or D, vector S or D, right? So when you have this kind of scenario, means that you're having conservation of force. Yeah. So what else is not conservative? If when you need to calculate the path, then it's not conservative. For example, friction. Friction, you need to calculate the distance it travel, the path it travel. The more you travel means more friction you have, for example. Okay, so this is a concept for conservation. It's independent of path, means it doesn't care how it moves, how many turn, or how many how it behave. Right. So for example, weight, that what you see on the screen here, weight A, position A to position B. So this one, W move down, W still move down, although the orientation a bit slanted, but W still point down. So in this case, the object move up, the work will be negative. Why work negative? Because you are multiplying two vectors. To get work, you take force multiplied by the distance that generate work. So in this case, the two vectors must go parallel. The work, weight multiplied by the distance traveled, start to end. Start to end. So you measure start to end. So actually it move up. So your distance move up, weight moves down. Multiply these two, you get negative work. Okay. If you're moving from B to A, then you get positive work because you are moving down, weight point down, both same direction, you get positive work. Okay, so this is a very important concept for static and also for other module that link you to the work. You need to use the work lah. So especially for that, for example, machine, fluid dynamics, all these things. Okay. So we just derive the work. So U equal to W multiplied by the R, right? The R. So if you can see from here, if you break it into a rectangular, so the R here actually do not 100% contribute to the work, right? Because you know that work can only exist when they are go parallel. So you split the dr into y-axis and x-axis. X-axis doesn't do work because x-axis is 90 degrees to the force. So you're taking dr cos theta, which is go opposite of the weight. Okay, so that's why it's the negative value there. to represent different direction. We are dealing with vector now. So you can simplify dr cos theta actually equal to dy. Okay. So in the solution later, you don't need to even know how to get dr cos theta. You only need to always remember, you always split the distance into parallel direction with the force that you are finding. Okay. So sometimes you can represent with h. It depends on the diagram. If diagram give you h, you use h. Okay. So the rest you read, the rest you read. Another one, spring force, also conservative. Okay. So spring force, you are dealing with the spring force here. So this is a undeformed position. So undeformed position, you pull it, right? You pull it to the right. You pull it to the right. If you are this object, you are feeling that the spring actually pulling to the left, right? So Fs equal to the distance traveled, right? So spring force is F multiplied by the Ks, right? Then if you want to do work, force multiplied by the distance traveled. So the spring force multiplied by the distance traveled. Okay. So why negative? Because the distance is moving to the right, but the force is pointing to the left. Okay. So you need to integrate du equal to minus ks ds. K you pull out, you put in the integration sign. So this side is u2 minus u1. Here, pull out the k. Here, the integrate s ds, you get s squared divided by 2. You'll get this equation. Okay. So you have half ks squared minus half ks squared, position n position minus early position. N position minus start position. Okay. So the work depends only the spring initial final position. Okay. Then this one is called conservation of force, conservative force. Spring force is a conservative force. Okay. Okay. Another one is friction. Friction is not conservative force because it depends on the path. It depends on the touching surface. The more you go, the more friction you have. Okay. So here, just let you know. So just remember, friction is not okay. So okay, so you will see spring, you will see external force, you'll see weight in your question, but you'll sure come across friction. So remember, friction is not conservative. Okay, potential energy, we deal with two types. One is kinetic, one is potential. Kinetic is half mv squared, potential is mgh, or in this case, we'll use wh. So potential energy, you need to be careful is maybe it's not mentioned in other module, but for static and dynamics, when you do potential energy equation, remember to start with the reference datum. Reference datum. Then if your object is above the datum, you will get positive potential energy because your H is positive. If your object starting position is below the datum, your potential energy is negative because your Y or your H is negative below the datum. Okay, so potential energy, you need to be careful, always look for datum. Okay, especially static and dynamic question, we like to give you a question dropping somewhere to somewhere. We always like you to ask you question from the high point to low point. Okay, so just take note on that. Okay, so you should be able to understand the positive, negative. Potential energy, just now it's force. Now we talk about potential energy generated by the spring. Potential energy given by the spring or any elastic rope or anything that can pull and come back to its original position is called elastic devices. So that can generate potential energy, elastic potential energy. We need to remember the potential energy for elastic will be half kf squared. Just remember that. Huh? Don't confuse this spring energy with work. Huh? Don't confuse this equation with the work by the spring. Huh? Okay. Potential energy of the spring always positive. Why? Because you have a square value there. No matter left, right, negative, positive, you square it, you still get positive value. Okay. Potential function. Okay. So potential function means potential energy equation. You need to depends on the question. If the question combine changes of location or changes of h, then you will sure have potential energy. If the question don't have spring, then you don't need to calculate spring. But if the question combine this one and this one, your potential equation for your solution, you should write all the potential energy for equal to gravitational force plus the elastic effect. So Vg means the H, the gravitational pulling force from the datum. Okay, Vg plus Ve. So this one is a general equation. If you see the question have changes of location from datum plus spring devices, or there's a pulling rope with the elastic, you're given K value, then you need to write V equal to Vg plus Ve. This, you write this one, you get 1 mark. Okay, or you write this one, then you write an arrow. If the question don't have spring, you just write an arrow 0. Don't have spring. For example, this one, the combination of block and spring. So if the block move from y1 to y2, y1 to y2, y1 here to y2 here, what is the work? What is the work done by the W and the spring? Again, datum is from here. So you write V equal to Vg plus E. So the work done by the W, the weight, is from datum to Y. Okay, datum to Y. Okay. Plus the potential, the work done by the spring. Okay, work done by the spring. Why this one y2? Y square? Because your Fs multiplied by the y, so your Fs is so this one you just apply the spring equation, half kx squared. The work done by the spring. Huh? Okay. Work actually is also means energy. Work also means energy. So you have the V, total work, total energy. So you can write U equal to Y2 equal to V Y1 minus Y2. So you can extend the equation into this one. Okay. Okay, now we go into frictionless connected system with 1 degree freedom. Its position is defined by position Q. This is just a derivation. Derivation. This one you read. We will cover this one in example. Maybe this one you might not see the thing. Okay, what is example is when a frictionless connected system of the rigid body is in equilibrium, we only interested in first derivative of the potential function equal to 0. So we only interested to get dy dx. In this case, your y is the v, the potential function, divided by the q, by the q. Okay, q is the changes of x, dy dx. Okay, so this one is a bit extended from what you learned previously in your physics class. Your physics class give you potential energy, but when you take the potential differentiate by the location, changes of position, you take it 0, you will get you can get the missing equilibrium position. Means you can get the y. Okay, you can find the y where it reach equilibrium position. Okay, so y equilibrium equal to work divided by k for this system, for example. Okay, so what is important for today class is this one. dv over dq equals 0 means the time differentiate, you do the differentiation to get equals 0. Y, if you look at this equation, is actually y equal to ax squared plus bx plus c. So a is positive, so you'll be like this. So you are interested to find this way. The point of this one is dy dx equals 0. This point is when you reach equilibrium. Okay, or if it's smiling face, it's a set face, also same. This is what we're interested in. Okay. So equilibrium also means this diagram where the force is all balanced. W is balanced by the spring force when the spring reach a position of y equilibrium. So there will be a one particular location when you press the object, when you put the object on the spring, there will be an equilibrium where you can find the distance of the spring go down. How much? To reach to balance the weight, for example. Okay. Okay, so another stability. When the question asks you about stabilities, there are 3 types of stabilities in equilibrium. If it's stable, then the point will acting on the center of mass. If it's nothing happen, no movement, then it's at a neutral. You will just stop there don't do anything. If it try to, like for example, this one, if you let go of this, it will either swing to the left or swing to the right. So this one is under unstable. Okay. So this one, if you hang it up there, so this one, it will just stay there, but there's a force balance everything in that particular position. So this is just an illustration of stable, neutral, and unstable. Okay. Unstable means when you let go of the object, it will roll over to one side. If you let go, the thing still stay at its original position, then it is unstable. Or you can say it's in the neutral. Neutral means no single movement. Okay. Equilibrium means if you pull this one to the left, you let go, it will still swing back to its original location. It will still stop at the point. This one, unstable, you let go, is either moving to the left, it will stop at the left. Moving to the right, it will stop at the right. This one, neutral one, you let go also, no movement. Okay, neutral means no movement. This one. So in the stable equilibrium, your potential energy in the system is minimum. Need to remember, stable equilibrium, your potential energy is minimum. Potential energy, there are three types. mgh, which is your H gravity force, and the spring force, right? The spring force, half kx squared. Yeah, only these two. Okay. Okay. So if the question asks you to find is in minimum, how you know it's minimum? dy dx equals 0 means you differentiate the potential energy, you get 0. Then it's either stable or non-stable. It will be minimum value, neutral, remain unchanged. So each time the disk rotated, new equilibrium position established, and the potential energy remain unchanged. So this one, potential energy, you still get back the same answer. Right? Unstable, potential energy will reach maximum. Okay. So how do you know whether maximum, minimum? You look at the curve here. On the left, stable means smiling face. Smiling face, you do dy dx, you reach minimum point. On the unstable is a set face. You do dy dx, you get maximum point. Dy dx 0, you get maximum value. Yeah. So if you plot graph, this is potential. This is V versus X. This is also V versus X. Constant. It will be the same. Remain unchanged. Meaning you dy dx, you will not get 0. You will get some value. There are some constant value, positive or negative. But this one cannot. This one, if it's 0, then it's either on the left hand side, minimum, or you go to the right hand side, maximum. How you know minimum, maximum? You substitute the value of this one, your x location. You substitute this one, this x location. You substitute, you can either, you get two value, one is maximum value, one is big number, one is small number. Because this is a quadratic equation. You'll get a quadratic equation for V equation. Okay, V equal to ax squared plus bx. You don't know whether your a is positive or negative, but when you do dy dx equals 0, you will get two answers. I'll show you in the tutorial question. Okay, so this one, during high winds and going around the curve, the sugar cane truck can become unstable and tip over because the center of gravity is high off the road when they are fully loaded. Means this truck go to the curve path, and if there's a wind blowing, so it might tip to the left or right. Okay, so this is what I mentioned. The curve for the V versus Q. Q is your location, your X. So you want to find the Q or the Y for the or the X for the stable condition. If it's this one, yeah. So your dy dx equals 0, you get one maximum point or minimum point. And if your dv dq you differentiate one more time, means second degree of differentiation, you get positive value. Positive value will give you smiling face. You need to do two tests, whether it's stable, neutral, or unstable. You need to do two tests. You get the equation already. You do dy dx one time. If you get 0, you either reach maximum or minimum. Then you differentiate one more time. If the value is positive, okay, how you know 0? Let's say y equal to 3x. Let's see, v equal to 3y plus 3y squared plus 4. Let's say, y is your this one, your q. So your dy dx, dv dy, or I'll just put down this q, dv dq, you'll get what? You'll get 6q, right? 6q. How you know the value is 0? When you substitute, okay, here you don't know, right? You don't know. You don't know whether this maximum, minimum. But you differentiate one more time. dv square, dq square, you get 6. 6 more than 0. So it is a smiling face. Of course, this one is your sketch, right? You don't like this one. So this one, you can just bracket and then smiling face. Then this one will be minimum. Minimum, then you know your Q value already. Q is something you differentiate, then maybe in this case is 0. You x 0 because equals 0. So your Q is 0, for example. Okay. Now, for example, this is just an example. This is an example. Okay. So you need to do two steps. Differentiate 2 times. One, it gives you, oh, this one is another one. Okay, so you do another one. So two process. If you get 0, dv dq 0, you don't not sure whether it's positive, negative, but you differentiate one more time. You will get that value whether negative or positive. So if it's positive, then it's minimum. If it's negative, then you get maximum. It's like you're solving a quadratic equation curve. Yeah, so these are the two procedures you need to remember. And then from here, you can substitute back the location of Q. Okay. So what happens if you have neutral? Neutral means your V value is constant value. If you plot graph, what I mean by constant value is a straight line. Okay, it's a straight line. So when there's a straight line, you know that dv dq equals 0. You differentiate one more time, straight line, constant value, you still get 0. Then you know that this is a neutral equilibrium. Okay, now? A two big procedure, dy dx, dy square dx square. From that two answer, you know whether it is stable, neutral, or unstable. These are the criteria. You need to explain why you say this one is neutral, why this one is stable, one is unstable. Okay, so if you understand this one, then we will go to yeah, this one is just let you know lah. If it's neutral, no matter how many differentiation you do, you still get 0 for neutral. So these are the procedure for your revision time. Go and read. Go and read. We will apply what we learn. Okay, so it tell you that this in equilibrium stability. It want you to find angle when it reach equilibrium. Equilibrium means work equals 0, all the force equals 0. Okay, or maybe the moment equals 0, but we rarely use moment. Investigate stability. Stability means three conditions: either stable, either neutral, or unstable. Okay, so you're given the mass, blah blah blah, spring unstressed when theta equals 0. So theta is 0 means this one on a straight line. This one 0. Okay, here you got spring. Right, you got spring. So you draw free body diagram, like what you see on the screen here. You need to know before, this is after. This is before, this is after. So you draw your diagram, free body diagram. You need to draw two diagrams. One is when the angle 0, you will see the gray color one. The gray color one, and you draw a datum. You establish yourself, this datum you draw. So you draw a datum before and after. The one you see on in the question is after. So then you need to build all the forces. So how you reach this one? You draw the wall first lah. Okay. Then you can copy the question. Because you draw properly. One is L, 0.6. A, B. Then in the answer, B at here. A will be on top. In here. Okay. So this kind of question, the first you draw all the length lah. Put in the center of mass, W, and 1, 2, theta. Then you put in all the parameter. Okay, so it asks you to find link, spring, unstressed. Okay, so the first one is the spring force. The spring force, unstressed is 0. So you actually pull the spring down from original location. So you draw from the spring original location. Then you need to draw the arrow. You know, draw the arrow S pointing down, because this is the end location. So when you have S, then you write spring force point up, because what you feel at this point. F equal to Ks. Then here, then the spring force you already find already. Then the weight will also do work. Okay, so you're only looking for conservative force. Conservative force. So W is here. So when it stand up 0 degree, it's at the half of the object. So half of the object, you just label from here to here is L divided by 2, or total length is L. Then when it's slanted at the end position there, you measure from datum here. So you need to find the height of this one. Height of this one is half cos theta, L divided by 2 cos theta. Okay. And then you do. Any question on the free body diagram? Okay. So then you write the potential function, because the question asks you equilibrium. So you write V equal to Vg plus Ve. Vg means referring to W. So here is L divided by 2. So theta. Sorry. Theta. Okay. We will continue. So weight, potential energy done by the weight is mgh, is the changes from starting to end location. In this case, your datum is here. So it changed from the object is changed. The object before and after is above datum. Before and after is above datum. So your potential energy for mgh is positive, huh? Because your date, all your object is above the datum. Okay. So here, spring will be half kx squared. In this one is y. The changes of y. So the changes of this one actually is same as the spring length. Okay. So you calculate, put the L equal to S plus L cos theta. Means this is the S, the length here, S plus here to here. Okay, here to here is, okay, here to here is actually L cos theta. Okay, L cos theta, or here to here, L cos theta. This is L. So this one is L cos theta. So here is S. Okay. Then you rearrange. You get S equal to something. Y you put in the L terms. Y equal to half L cos theta. You put inside there, substitute back here. This one, you just need to remind yourself to change all in the same length as inside the question. Then you substitute back, you get one equation. So this equation you see is in the form of ax squared plus bx plus c. So again, how you know is equilibrium or not equilibrium, or not stable or neutral, you do differentiation 2 times, 1 and 2. Okay. So first derivative give you dv d theta. just now you still Q, right? So in this case, we are if you are using theta, so we differentiate with theta. So this one, you go home and see how you do trigonometry differentiation. So straight away give you the answer. Differentiate. Oh, okay. So you arrive at this equation. Arrive at this equation. L cannot be 0. Theta cannot be 0, right? Because all this, okay, this whole thing, how this whole thing can be 0? Either this whole thing 0 multiplied by this one, you get 0, or this term itself is 0. Makes sense? You look at this equation. So how does this equation become 0? There are only two scenarios. This L cannot be 0, you know. So this bracket one, either 0, then you take 0 multiplied by sine theta, you get 0. Or this one is not 0, then this one must be 0. Okay. So equation certified when you have these two equations. So sine theta 0, sine at what degree equals 0? Sine 0 equal 0. Okay. Sine 90 equal 1. Okay. So, or this one equals 0. There are two cases, right? So you know that 0 is when before it start, right? Before it start. Or another side is equal 0. So when this one equals 0, you rearrange, you get the angle equation. In this whole thing is 0. You will get theta equal to something. Okay, you substitute, you'll get angle equal to 1 degree. Okay, W, you know, you're given the mass mg here. K is given, there's K given. K given. K not given. Got lah. 200 Newton over meter. Okay, in the question. L, you know, L is 0.6 meter. Okay. So when you know angle, what does the angle tell you? It's in the equilibrium position. Means this at this angle, even you do all the y equals 0, you will get this angle. Or you substitute inside there, everything will be 0, equal to 0. Okay, stability, you do second derivative, dv squared d theta. So take back just now, the first derivative, you arrive at this lengthy equation. You differentiate, you get second equation. Go home, do revision on the differentiation on trigonometry. We don't have time to explain to you how to do the thing already. Okay, so you arrive at one very lengthy equation. In this case, what you can do, the next step is you factor the cos or sine out. You factor out, you get one big bracket, cos theta. You know what I mean, right? So this one, you got cos theta, pull out. This one also you pull out. Okay. So you put in, or maybe you don't need to do anything. You just substitute the value in the just now. Just now you find equilibrium 53.8, right? You substitute inside there. You get 0. What does it mean? It is what? The three cases, right? Stable, neutral, and non-stable. So dy dx equals 0. You don't know. but d square y dx square, when more than 0, this is stable, equals 0, it is neutral, less than 0, you get non-stable. All these are 0. Huh? So in this case, you already proved when you can substitute value constant, these two values. Okay, you substitute there. Huh? Substitute two value. One is 53.8, one is 0 degree. So when you substitute at 53.8 degree, substitute inside here, you get 46.9, more than 0. So it will be stable, equilibrium. Okay. When it's degree is 0, you substitute inside here, you get negative. It means unstable. So when it reach 46.9 degree, is stable. So when you pull to the standing position, it is not stable, because once you let go, you know that the roller will push to the left, right. This is how you prove mathematics through static equation, entering statics. This is how you prove the system stable, not stable. Clear? Okay, example 6. If you understand already, example 6, your homework, go and have a look. So I won't explain more. Example 6 is more on the question 2 for your test 2 or final exam question kind of standard. Okay, it's more on application. Okay, example 6. But you see the steps, you see the step always same. Observe the step. You draw free body diagram and then find the VG, VE. In this case, got spring, so you need to find the VE. After you find the total of VG, VE, you do differentiation. First differentiation, second differentiation. You'll find one angle, equilibrium here. You have two angle actually, because this one is actually by trial and error. You don't know. You just keep on trying. Okay, this is a very complex, not complex, but very troublesome question. You won't see this trial and error kind of question in the test or final exam. Okay, but this is one that we're showing you because you will see this one in the industry later. When you graduate, you will come across this problem. Okay. Again, nowadays you have ChatGPT, you have all the AI system. You just put inside there, help me to solve this equation. First derivative, second derivative. It will run at the background. Maybe it takes you maybe 5 minutes to give try and round. Then it will give you 2 answers. Okay. So this one will be the future education. We no longer need you to list a lot of long piece of answer, but we want you to know the way of finding answer. That is more important. Okay. So stability, you find out. If you get negative, then unstable. You get positive, means stable. Okay. Example 7 also same. This is no value, but you need to solve using parameter. Okay. So in final, I love to ask question something like this. I will remove all the value. You give me answer in ABC or MHR, something like this. So this one, have a look. I have a look. Okay, example 7, have a look. But same, but still same. You see, first step is you find V equal to VG plus VE. So in this case, you don't have spring, so 0. Then the rest you find for MGH. This one you got one object. So equilibrium, then you solve for dy dx equals 0. Then you solve for dv squared d theta. How you know the value? You substitute the value from here, from the first one. Okay, you substitute there, you either get positive or negative or zero. The only three conditions. You substitute there. Then from here, how you know it's unstable? You look at this equation. Negative, negative value. Negative, negative value means negative value already. Multiply by positive value, you will get negative value. So it's an unstable thing. So again, I like to ask questions something like this in finance. Okay, so you need to have a basic understanding on the equation that you write in your answer. You need to know what does it mean? Okay, and also it's an application of what you learn in your mathematics. Okay. Okay, so with this we conclude chapter 6 already. Okay, any question? A question?